All right, welcome everybody. Let's begin. A couple of important announcements. Now, homework number 3 is due on Wednesday, and I'm going to be giving you a demonstration in class today on how to use Microsoft Excel. It's a pretty simple and straightforward example, so I don't think you'll have any problem incorporating what you see today into the homework that's due 2 days from now. But I did want to point out that the last question on the homework assignment is something related to Excel, and probably if you've already looked at the assignment, you may have been wondering about that. So we'll touch on that today. Now, on the subject of computers, please bring your computer to class on Wednesday. We're going to start using Microsoft Excel pretty extensively, and of course you can get free access to the entire suite of Office products through Microsoft 365, which they have here on campus. So bring a laptop to class on Wednesday, and if you don't, then you'll just have to scoot up to next to somebody who does have a computer and observe them do the work. And it's not nearly as engaging, and you won't get as much out of the class meeting if you don't have a computer with you on Wednesday. If you don't own a laptop, they check them out from the library. They have a limited number of computers that you can check out, so that's one option that's available to you. Any questions about these announcements? All right, so today we're going to go through some techniques that we can use to solve for other things besides P, F, A, and G. Most of what we've done so far, you've been solving for an amount with a given number of periods and with a given interest rate. But sometimes the interest rate or the number of periods is the unknown. And when it is, the computational techniques can be a little bit more difficult, and so that's why we can turn to the computers. It simplifies things compared to if we had tried to solve it by hand. So solving for I and solving for N is what we're doing today. But first, remember that this is what we looked at on Friday with that in-class exercise where we had both a gradient and an annual series together. So this is the cash flow diagram that you were given. And what I wrote on the whiteboard and then later showed you in the PDF that I brought up on the screen is that you can break apart this original cash flow diagram to its two component pieces. The component piece that has the annual series and the part of it that is the gradient. And so if you're solving for P overall, then the cumulative total P would just be the present value of the gradient part and the present value of the annual series part combined together. Okay, so that's just to set the stage for what we did last time. Now, this gradient, remember, the first time we see evidence of a gradient is in year 2, because in year 1 it was 0G. So there's no dollars that are being added to the cash flow diagram at time 1, because 0G just means whatever G is, 0 times that's going to be no money. So I wanted to refresh your memory that time 0 is 2 periods forward of the first time that you see the gradient. 2 times earlier, 2 periods earlier. So it's here at time 2 that you see the amount. That means that the present is 2 years before that. In the homework, I give you a gradient that's shifted forward in time. I don't think it's exactly this, but this is just an illustration of the essence of that problem on the homework assignment, which is where you have a gradient, but it's a couple of years beyond, forward in the future, of this earlier example, where the gradient began at time 2 and 0 was 2 years prior to the gradient. So this is more of what that homework problem looks like, and what I'm asking you to do is find the present value of a gradient, but what we know about a gradient is ordinarily we would call time 0 2 periods before the first time you see G. So I'm just now, for the first time, introducing to you the idea of a quasi-present. Something that just temporarily we're going to consider as year 0 from the perspective of the gradient, And then once we move the value of this gradient to that quasi-present, then we'll move it from that year to the actual present. So here's what I mean. This is year 2, right? From the perspective of a gradient, it's 2, 3, 4, 5. And so that would mean that from the perspective of the gradient, time 0, and I'm using my fingers here to denote air quotes, time 0 is actually here at year 3. So what you could do in order to find the present value is you would take the value of this gradient to a lump sum at year 3, and then as a second step, you move it from year 3 to time 0. So in that second step, this arrow would now look like an F, because it's in the future from the perspective of this being our present. Okay, so step 1 is consider the gradient, find P given G. So step 1, find P given G, and by P, what we mean is some lump sum amount at year 3, because that's the quasi-present. You see how it's got the quotes here? That's the quasi-present from the perspective of the gradient. And then when you have that lump sum at year 3, then you would consider this arrow as an F. So we're no longer in the second step, we're not calling it a P. In the second step, it's just some amount in year 3 that needs to go to 0. And so this is F, this is P, and we would find it as a lump sum amount at time 0. Yeah.
So then it would be like once you get to the second step, you would like do an equation where it's like P given F, or.
Yep.
And then
find P given F.
The other thing I was gonna say, like if you were doing an equation where it's like you're trying to find the gradient at like the quasi-present or whatever, what would n be? Would it be like 8 or would it be 4? Or?
Good question. So what is n in that first step where we're finding the value of this? It would be, so this is 0, 1, 2, 3, 4, 5. So n is 5. From the perspective of this being time 0, we would come up with like a quasi, I mean, you can write it down like in a secondary location if that helps you to see it. You know, you could just underneath here in like faint pencil do 0, 1, 2, 3, 4, and 5. And then that would help you to see, you know, here's our quasi-timeline with n equals 5. And then you'd find that, and then it would be n equals 3 for the find P given F, second step. Thanks for asking that question. That's a really good point. I'm glad you raised it. I'm giving you all the hints today, all the homework hints. All right? All right, so in the book, we've got this series of equations. And remember that inside of the parentheses, the first term is the ratio of what it should be known as equal to on the right-hand side in this formula. So P slash F, what that means is the ratio of the future, I'm sorry, I said that wrong, F slash P. It's the ratio of the future value to the present value on the left-hand side of the equality, and on the right-hand side of the equality is just what's in the rest of that table. So A divided by F is equal to whatever you'd calculate here, and so on and so forth. And then it's with these interest factor equations that you can be accurate to the nearest penny by not rounding off as you are calculating the factor in your calculator. But when you use the tables that are available in the back of the book, then you have to be sensitive to how many digits of precision are provided in that factor. All right. I've already used the idea of balance a couple of times so far this semester when I'm talking about equilibrium between amounts in the future and amounts at the present. And I've talked about the idea of the time value of money and economic equivalence. So for example, the economic equivalence of either getting $100 now or $110 1 year from now if your interest rate is 10%. Those two amounts are economically equivalent. So it would be in balance if you deposited $100 today into an account that pays 10% interest, and then you withdraw $110 in 1 year, that would be in economic balance. The inflows and the outflows would be in equilibrium according to the time value of money. So this cash flow equilibrium is sometimes what we have to be using as our goal for finding unknown interest rates or unknown amounts or unknown number of periods. Sometimes I'll give you a problem and I'll say, how much would you have to pay today in order to justify this series of payments you're going to get in the future? You know, these are the ideas related to how much should you spend to purchase a business. That's an idea of economic balance and the cash flow equilibrium. The present value of the inflows being equal to the present value of the outflows is what we'll sometimes be solving cash flow diagrams in Microsoft Excel. We'll be looking for the two things to be in balance so that we know that when it is, the interest rate is the unknown interest rate that is related to the rate of return for the project. So it's essentially how much you're earning on the project when those two things are in equilibrium. So for example, if you paid a lump sum of $23,000 now at the present in order to purchase some business that's going to give you revenue over time. So in this illustration, you'd have $5,000 of revenue in each period for a total of 6 periods. So the number of dollars isn't equal because 6 times 5,000 would be $30,000 in inflow. But of course, we know that money now is more valuable than money in the future, and so that's why you should demand a greater number of dollars in the future than you invest today, because you want to have some rate of return that's going to justify the fact that you are spending more valuable dollars to get less valuable dollars. So you could solve for the interest rate that makes this an equilibrium. Is this cash flow diagram in balance? The only way you know is to solve for I. And so the way that we solve for I is we keep iterating over and over again. We look for the interest rate that makes the inflow equal to the outflow. So if I equals 0%, then this isn't in balance. Because if we took the present value of this annual series, so find P given A, at 0% interest, it would be 30,000. And so 30,000 is not equal to 23,000. So that would tell us the interest rate isn't 0, it's some non-zero positive amount. And so we'll go through the process today of trying to solve for the interest rate that brings balance between inflows and outflows. So that's the conceptual foundation for what we're doing today with the in-class exercises. We're going to be looking at a variety of different interest rates and different periods that makes inflow and outflow equal. And our process in this will be that you'll be given some cash flow diagram or a cash flow statement in English language, and you'll discount all the amounts in the future to the present. So this annual series would be taken to time 0, and you discount it at either a given interest rate or at a guess interest rate if you don't have a given interest rate. If you're trying to solve for an unknown I, you just start with a guess. And you'd combine it with the amount that's already at the present. Oftentimes that's the lump sum outflow, the expenditure that you incur to purchase a piece of equipment. And then you'd keep changing your guess value of I until there's balance between the inflow and the outflows. So that's the computational process that we'll go through when we start up Excel. Now, when I'm using Excel, I'm going to have to manually override an assumption that Excel has. Just the way that Excel works is it assumes, for example, that if you put into one of its equations a positive amount, it should return a negative amount because it's assuming that you're doing calculations of the sort where you do a deposit and then you later on take a withdrawal. So it's automatically going to change the sign. So in other words, if I know I'm going to receive $12,500 in year 3, I could have Excel calculate the present value for me. If I just told it some interest rate, it will calculate P. But it's going to return a negative number when it calculates P, because it's automatically assuming that if I'm getting an inflow in the future, that must mean that I have to do a deposit at the present. And sometimes that's true, sometimes that's what's happening. But in other cases, we may actually want to know the magnitude of the amount, but not necessarily have Excel changing the sign. So I'm just going to have to keep that in mind, that Excel will take a positive and turn it into a negative. And so if I really just want to know the magnitude of the amount and not necessarily have it change it from an inflow to an outflow, I'll have to manually put a negative sign in the equation to override what Excel's default assumption would be. So Excel has some pretty handy built-in economic formulas, and it saves us a lot of time when we use them. But if we misuse them and don't understand the built-in assumptions with these built-in formulas, then it can get us in a little bit of trouble. So I'll help and reinforce that idea that we need to put the negative sign in when we're using the pre-formatted equations. That negative sign will be manually put into the formula. All right, so hopefully you've got in-class exercise number 9 printed out. Let's take a look at what we're doing here. In-class exercise number 9, I've provided you with 2 factor tables, the 10% factor table and the 12% factor table. And there's a statement here. A contractor purchases equipment for $60,000, provides an income of $16,000 per year for 5 years. Okay, now the first part, I'm asking you to draw the cash flow diagram that summarizes that description. And then using these tables, the 10% table and the 12% table, find the net present value. Net present value means what's the present value of the outflow combined with the inflows. So find the value of the annual series and combine it with the value of the amount that's already at the present. So do that for 10% and 12%. And once you've gone through this manually, I'm going to bring up Excel and give a demonstration on how we can solve for this using the spreadsheet. Okay, let's take a look at the solution to part B and C. Well, I guess, and A as well. Here's the cash flow diagram where we have an outflow, so the arrow is down in the amount of $60,000 at time 0. And then we have 5 equal height arrows representing an annual series in the amount of $16,000. All right, find the net present value. That means what's the present value of the inflows and the outflows. That's what it means by net present value. So what we do is we go to the table and find the P/A factor for the 10% table and n equals 5. So here's the 10% table, n equals 5, and P/A is 3.7908. So with that factor, 3.7908, multiply it by 16,000, and that's, here is the value of the revenue. So the present value of the revenue is $60,652.80. But then you have to combine that with the present value of the cost. So combining it with the $60,000 outflow means that the net present value, meaning combine together the inflows and the outflows, is the present. What is the value of the present value when you put it all together? $652.80. And we can be accurate to the nearest penny on this one because we've got 5 digits in the factor. 1, 2, 3, 4, 5. 3, 4, 5. Well, maybe only nearest dollar because of the 60,000. In any case, it's a positive value. And now, similar approach for 12%. This time the factor is 3.6048. So the present value of the revenue is 57,676. And then you combine that with the outflow, and this time we have a negative present value. So let me tell you what this means. It means if you could borrow money and pay 10% interest in order to borrow it, this project is profitable. So you know the $60,000 that you have to spend at the beginning in order to buy this item? If you borrowed the money from the bank to buy the equipment, but then you're going to pay some of your revenue to the bank to cover the cost of the loan, and then part of the revenue you get to keep for yourself as profit. If you're borrowing money at 10%, this project is profitable because you have a positive net present value. But if you have to pay the bank 12%, then this project isn't worth doing because the sum of the present value is negative. So that's kind of the physical or the real world interpretation of what it means to have a positive versus a negative present value. Any questions so far on this hand calculation part? All right, so in problem D, it says that you should observe the solution using this following method that uses the sum of the present value of the amounts are equal to 0. So let me start up Excel, and I'm going to remind you as I begin that this lecture video will be posted on YouTube. So if there's some certain part of the illustration I'm about to do that you miss, you can go back through the recording and see it there. Now here at the top, I'm going to define an interest rate. So I equals, and I'm just going to type in the 10% so we can check to make sure if I get this set up correctly, because we already know what the answer is if it's 10% interest. We just solved that by hand. Remember, I have to put the interest rate in as a decimal. All right. Now here I'm going to have a column that is for the year, a column for the amount of the cash flow diagram, and then another column where I'm going to calculate the present value of some amount. All right. So the year starts at time 0, so 0, 1, 2, 3, 4, and 5. So this first part, all I'm doing is I'm translating the cash flow diagram to a cash flow table. So here's the cash flow diagram, and so for the cash flow table, I want to have negative 60,000, and then I want to have 16,000. And rather than typing that over, if I just type it twice, then I can highlight these two, and then down here on the left edge, see where it's a little bit thicker green? I'll click and drag that down, and it continues the same pattern of 16,000 multiple times. And that saves me from having to type it over and over again. So that's nice. I'm going to format this as amounts. Over here where it says number, I'm going to, in the drop-down box, I'm going to have it say currency. All right, so now I've got the amounts with the dollar sign there, and it's got the negative sign in front of the outflow. Okay, now I'm going to use this formula, a built-in equation that Excel knows. So the built-in equation is equals, is how you tell Excel you're beginning an equation with the equal sign. So equals, and I'm going to type in PV. And it starts to, below here, give us an indication that it knows something about the PV formula. It's explaining what the PV formula does. See how below that it says returns the present value of an investment? And as soon as I put in this parentheses, it starts to prompt me on what it needs to see in order to use this formula and in which field. So in bold here it's saying rate. So it's telling me what's the interest rate. Okay, so I could either type in 0.1 because our interest rate is 10%, or I can just click in this location. So I'm going to click in the location where it's got that interest rate. Okay, And now comma, it's saying NPER. That means the number of periods. So in our example, there are 5 periods. So I'm just going to type in the number 5. So there's 5 periods. Now, this next field, it's saying payment. And you'd put an amount in there if it was a recurring payment that's happening multiple times. But we're going to treat each one of these rows as though it's a single, isolated, individual amount that we're discounting to the present. So I'm skipping over that field, just putting in another comma. So as soon as I put that other comma, it skips over the payment, and now what's in bold is it says future value. Okay, so I need to put a negative sign because of what Excel always does with changing the sign of things, like I was explaining to you earlier. Put the negative sign, and I'm clicking on the location where I've got an amount. So this is going to tell me what's the present value. Oh, you know what? I put in the wrong amount for the NPER. I'm glad I noticed that. It should just be year. All right. Because this 60,000 is already in the present. And so it needs to be moved 0 years to get to the present. All right. So when I close the parentheses, as soon as I press enter, it's going to calculate what's the present value of $60,000 that's discounted at 10% per year, and it's going to discount it 0 years. So it's just going to be the same amount as it was before. It's just going to tell me 60,000. It's in red because this right now is formatted according to like an accounting style that puts positive amounts as black and negative amounts as red. I don't particularly like that, so I'm going to just click on currency and it'll take it back to the default formatting where it doesn't have the parentheses and the text isn't in red. All right, now I need to do one other thing, and then I can, well, let me show you if we were going to repeat it just for the practice, because this is maybe the first time you're ever seeing these built-in functions used before. So just to refresh your memory, it's equals PV, and that's what tells it we're calculating the present value. The rate, I'm going to click up here in the interest rate, and I'm going to press the F4 button. And when I press the F4 button, it's going to put a dollar sign in before the B and before the 1. And what that's called anchoring it. And I want to anchor the reference up here to this interest rate because when I drag the formula down, I always want it to look in the same spot for the interest rate. I don't want it to look in the next cell lower when I drag the equation down. All right, so the interest rate is 10% and it's locked to cell B1. Okay, I'm going to put a comma. So NPER, the number of periods, 1. So it needs to be moved 1 year back to get this amount to times 0. Because this 16,000 is 1 year ahead of times 0. Okay, I'm going to skip over the payment field, and then I'm going to click on the amount in the minus of the future value field. Okay, so now let's see if this makes sense. 16,000 in time 1 is the same as 14,545 at time 0. So it's taking this 16,000 and it's discounting it 1 year. And if I drag this formula down by, see where it's a little bit thicker green in the lower right part of that cell? If I click that down, then these amounts are getting progressively smaller because n, the number of periods it's being discounted, is going up. So this is like saying 16,000 in year 5 is worth 9,934 at time 0. So it keeps getting smaller because this amount has to be discounted more and more years. All right, so then the last thing I'm going to do is I'm going to add it all together. So if I do equals sum, and inside the parentheses I'm going to click so that it includes the range of all of these values. 652 $6.59. So let's see, is that familiar? $6.52.80. So it's pretty close, but remember the difference being that this was using a factor, whereas this is using the equation method, so there can be a slight round-off issue. Now what about the 12%? Remember when we did 12%, we got negative 23.23. So let me change the interest rate here to 0.12. Negative 23.23. That's pretty powerful. What we've done is we've set up this spreadsheet so that all we have to do is change the interest rate to any value we want, and it's automatically going to return the net present value of this series. So any questions so far? We've replicated our hand calculations using Excel. I know if this is the first time you've really used Excel, that could be a little bit overwhelming, but it'll come naturally. We'll get enough practice with it that by the end of the semester you'll feel very confident. All right, so observe the instructor's solution using the method sum of the PV of the amount is equal to 0. All right, so we want to find I, because I, the amount that brings balance between the inflow and the outflow, is between 10% and 12%. What we saw from these hand calculations is that 12% is too high, 10% is too low. That the answer to like what interest rate makes the inflow and the outflow equal, the answer is somewhere between those two. It's the crossover point where the inflow and the outflow is equal. So if I keep changing this interest rate, I want to find what interest rate makes that 0. So 0.01. That's way off. 0.1. Getting closer. What about 0.11? Okay, I'm in negative territory. So it's somewhere between 0.1 and 0.11. What about 0.105? Getting closer. I want to get this so that the sum is 0. So what about 0.111? That's the wrong direction. 0.109. Closer still. Now it can get pretty tedious if you just keep typing that in manually. So there's something we can use, a goal seek function in here. So it's on this data tab. Data, what if analysis, goal seek. And I want this to be equal to 0 by changing the interest rate. So I've told it, I've given it permission essentially to, in an automatic way, it's going to try a lot of different values of interest rate. It's just going to randomly go through and try a bunch of different I values until the amount in this cell, C11, is equal to 0. So that's the definition of a goal seek. Its goal is for cell C11 to be equal to 0. And what it can change to achieve that goal is the amount that's listed in cell B1. So as soon as I click OK, it's going to be so fast you won't even be able to see it. It's going to go through really quickly, and you may see a little bit of a flicker in cell B1 as it goes through the numbers, and then it'll stop. And this sum will be equal to 0 because it will have found the interest rate that brings balance between the inflows and the outflows. Okay, so here I go. I'm going to click OK, and it did it. It found that 10.042, and look at all this precision here, 10.4% is the interest rate that makes the inflow and the outflow equal. So in other words, if you had to borrow money from the bank, and the bank's charging 10.42%, the project isn't going to lose money, but the bank would get all of the profits. If you had to borrow the money at 10.42%, then all of the extra revenue you're getting in the future is just going to pay off the account. All right, so you've seen a lot just now. You know, if you're unfamiliar with Excel, then you've just definitely got sprayed in the face from the fire hose of information. There's one other way to solve this. You have to know how to do it this way. So on a couple of occasions in the semester, I'm going to give you test questions where you have to be able to do it this way. And on the homework, you have to do it this way. But there's another method called the rate equation. So here in the in-class exercise, it says observe the instructor's solution using equals rate. Okay, so that means we can just do equals rate parentheses. Now it's going to give us a few prompts. NPER. Does anybody remember what NPER stands for? Number of periods. Okay, there's 5 periods. Okay, payment amount. Our recurring amount that, you know, the revenue that happened over and over again was 16,000. So let me type in 16,000. Or I could click in a cell that has 16,000 written. So I could just click over here, 16,000, and it'll look at the amount in that location. All right, and now PV, it's what was the amount that was at time 0? Negative 60,000. So let me click in that cell. And then I'm going to close parenthesis. And it says 10%. I'm going to increase the number of decimals that are shown here. 10.42%. So it kind of just repeated that process of setting up this table and going through and solving for I. In an automatic way, it repeated that entire workflow that we just went through manually. So if you want to check your work, you can use that rate equation. But for a variety of reasons, because this approach is applied in some additional problem solving, you have to know how to do it this way, because this rate method doesn't always get you where you need to go. All right. So that is question 1. All right, let's take a look at problem 2. Unknown N. A contractor purchases equipment for $60,000 that provides an income of $8,000 per year. At 10% per year, how many years until the investment breaks even? All right, so P is 60,000. A is 8,000. Because it's a recurring amount. So the ratio of P to A is 60,000 divided by 8,000. That's the ratio. If we find that amount, it's 0.1333. If you actually do the ratio of A to P, let's see, did it ask, okay, what's P to A? So I guess it would be the inverse of that. I have this from a previous semester when I have the other way around. So 60,000 divided by 8,000, 60 divided by 8 is 7.5. So now in the column of P to A, look for where does it cross over. Where would 7.5 be? It would be here between the 14th and the 15th year is where it would go from too low to too high. So that's the number of periods it would take to achieve break even if you're getting $8,000 of revenue each year. So that break even point is what's being asked for in this next example of how many years until the investment breaks even, meaning how long until you've paid off the $60,000 if you've got a 10% per year loan and you're getting a revenue of $8,000 per year. So from a table, you just look for the crossover point for when the ratio, where would the ratio of P to A be? So the ratio that we'd look for is 7.5, and it's between the 14th and the 15th year. Now, using Excel, we can find a similar thing. Let me start a new tab here, a new sheet, and show you how we would solve this one. Again, I'm going to start off by defining an interest rate, and the problem statement tells us the interest rate is 10%. So 0.1 is our interest rate. And then down here I'm going to have year, amount, PV of amount, and then one last column that's new. It's called cumulative PV of amount. All right, so year starts at 0. And let's just continue this through like 17 years just so we make sure that we see the crossover point. So here's the numbers. The amounts is that we pay $60,000 at time 0, and then we have $8,000 of revenue each year. So that's a repeating amount onward through time of 8,000. I'm going to format all of these as currency. Remember how I like to have it as currency with the dollar sign? Okay, PV of amount equals PV, the rate. I'll click up here and press the F4 button to have the dollar signs in front of the B and the 1. N is just which row you're in, so the year. I'm going to skip over the payment field with a double comma and then minus of the amount in the field for FV. So the 60,000 at time 0 is going to stay 60,000. And then if I drag this down through the rest of the table, you can see that the amounts are gradually getting lower and lower and lower because $8,000 further in the future isn't worth as much in today's terms. So that's why the present value of the amount is getting smaller. Okay, last thing. Cumulative present value of the amount. Starts off with just the amount, and then for each subsequent year, it's the previous year's amount plus the PV of this year. So I'm adding the cell above and the cell to the left. And when I do that and continue the trend downward, it's going to cross over from negative to positive between the 14th and the 15th year. So what that means is that after 15 years of operation, then you've paid off the equipment and the project is profitable. It's 11:50. We're out of time for today. It's this first one that you have to be able to do for the homework assignment. So if you have any questions, let me know. I'll see you on Wednesday.